one of those. P's, 3. D's, 5. And F's, 7. And this is like when we were doing the quantum stuff. And so we said, well, if we have a P, then it's going to be 3 lines. And that's why we have this 3 here. So when we drew D's, they had 5 lines. Do you remember that part from earlier in the semester?
Yes.
Yes.
Okay. All right. So that's why S is just 1, P is 3, D is 5, and F is 7. So we're going to start with the carbon right here that I'm turning green. All right. And I'm going to look at all of the atoms that are attached. So there's 1, 2, 3. So I'm going to turn them all. Actually, I shouldn't turn them green. I should turn them like, I don't know. Not red. We already used red. Purple. Okay. So this one's attached. This hydrogen is attached. And this carbon right here is attached. They're all attached to the green carbon. So that's 3 things. So what you're going to do is if you hold your hand up in front of you, put down your finger and your little finger, and just, I don't know why I'm explaining this. Hold up 3 fingers. Sorry.
Okay, 3 fingers.
Yeah, hold up 3 fingers.
Oh, good.
And then you say S, and you'll put 1 down. P.
Okay, S.
Mm-hmm.
P.
And then put the second one down. And then SP2. So S, P1, P2. And when you say P2, no more fingers are up.
Correct.
All right. And so once all your fingers are down and you stop, that's the answer to what the hybridization is. So in this case, we said S, then we said P1, then we said P2. So the answer is going to be SP2. And the 2 should actually be an exponent, but I can't do that in Zoom. I can't figure it out, so we'll just leave it there. So that's how you figure out what the hybridization is. Now, if you notice, there are 3 p orbitals. If you look down where I drew all of those little lines down there. So when we have sp2, we have a combination of an s orbital and 2 of the p orbitals. So those are going to hybridize and become kind of like a Frankenstein group of orbitals. There will be 3 of them, and they'll each be sp2 orbitals. So instead of there being an s and 2 p's, they'll be sp2. They'll all 3 be sp2s. But you'll notice that we have this 1 left over. It's just pure p orbital. The pure p orbital, you can see where it is in the model up here, because it's the double bond. The double bond is the pi bond, and pi bonds are made by pure p orbitals. So when she said it has to be S, then what that means is it has to have 3 things around it. And remember that the things that count are either atoms bonded or lone pairs. For example, if I had something like this, then I would still put up 3 fingers, one for the first hydrogen, one for the second hydrogen, and one for the lone pair. And those would be sp2 also.
Okay, so like when you are counting the different orbitals in that shape,
Uh-huh.
how do you know like which hydrogens you would count from, like on the left or the right side?
That's a good question. It just, in the case of being aromatic, all of your carbons have to be sp2. So you want to go all the way around the ring. It doesn't matter where you start. You just start on one of them. I like to start at the top just out of habit. And when you do that, do an orange, you start by looking at the carbon, and then you look at the things that are directly attached to it. So you kind of like draw the line down here. That's one thing. There's a second thing. And then your third thing, and that's how you know what to count. So you count everywhere you drew a line to connect it to something. And then with the next one, oh, go ahead.
And then it would just be like the same thing on the other sides, correct?
Correct. You would do the same thing. Like, for instance, with this carbon, you would draw a line to that hydrogen, a line to this hydrogen, and a line, not hydrogen, a line to this carbon. So to this carbon, to this carbon, and then to this hydrogen. And so that's 3 things as well. And anytime you have 3 things attached, that's always sp2.
Okay.
Did you want to show me the rest of the video?
Oh yeah, sure.
Okay. Let me stop sharing. All right, go ahead.
Share screen.
Third and final piece is that you're going to have an odd number of pi cloud electron pairs. So let's see what this looks like in practice. Okay, so now let's systematically apply these 3 rules to each of these 4 compounds to determine whether or not they're going to be aromatic. So if we take a look at this first compound here, we see that it meets the first criteria. It does have a cycle in it. The second criteria is that it has to be planar. And if we take a look, all of the carbons that are participating in this cycle here are sp2 hybridized, which would mean they would be planar. Remember that this carbon here, even though it's sp3, doesn't impact their aromaticity because it's not directly part of this ring. The third rule is that we need to have an odd number of pi cloud electron pairs. So here we have 1, 2, 3. So this one meets all 3 criteria, so this here would be an aromatic compound, a really stable compound.
Okay, like so when she said like an odd number of pi electron pairs, so is she counting them by like 1, 2, 3 or 2, 4, 6?
She's counting how many double bonds she has.
Oh,
So she's saying, I have 1 double bond, 2 double bonds, 3 double bonds.
okay.
That's a good question.
Let's take a look at the second one. So it's got the cycle, so good on the first criteria. The second one has to be planar. So we can see that all of the carbons that are participating in those double bonds would be sp2 hybridized. These ones here, though, would not. They both have 2 hydrogens implied coming off of them, so they would be sp3 hybridized. And because of that, this would not be a planar cyclic compound, so this one here would not be aromatic. Let's try again on the third one. So here, cyclic, it is. It may look like a square, but that's still a cyclic compound. The second criteria, planar. All of these carbons are sp2 hybridized, so we're doing well so far. The third criteria, an odd number of pi cloud electrons. In this case, we actually have 2. So this would be a different kind of compound, and it would be called anti-aromatic. So whereas aromatic compounds are
So what do you think about the last one? Do you think it would be aromatic?
Hydrogen coming off. And if you count 1,
I don't think so.
3, 4 areas.
You're correct. It's not.
Typically, that will be labeled as pretty. But now this is the thing, right? We have all these rules to help us understand molecules, but they don't follow our rules. And they do whatever leads to the greatest stability most often. So in this case here, if this one adopted an sp2 hybridization, then it would have 1, 2, 3 pi cloud electron pairs, meaning that would make it aromatic. And that actually is what this compound does. So this one may not look it initially, but this one would follow.
Yeah, that one I didn't get.
So it's pretty
Yeah,
much how you apply the rules to a compound is aromatic.